Also, I welcome our faculty members from Physics department and chemistry department and other departments. I welcome our scholars. I thank you all for your presence here. Also, I thank our management, Director Madam Kushal Sir, for giving the opportunity to organize this faculty development program on materials research. Today we have chosen the topic advanced materials research because materials research is inevitable nowadays. Because only new findings in the materials only useful for the development of the technology. So we have chosen this topic. So this will be useful for all the faculty members, especially faculty members in physics and chemistry department. Also our PhD scholars. So first Dr. P. Krishnan will deliver his lecture on mostly he will talk on the nanotechnology and magnetic materials. Next, Dr. Padmavati will deliver on fuel cell technology. So both the sessions will be useful to all of you. I request you all to listen carefully and utilize. Thank you very much.
Share it out.
Now I request Dr. Mary Angeline Madam to deliver the memento to our guest, Dr. Krishnan. I invite Dr. Saravanan sir. I request Dr. Vadivel, HOD Material Physics. I request Dr. Arnav sir. Now I request Dr. Associate Professor in Physics, St. Joseph College. He will deliver his lecture on materials technology. Now
फ्रंटला बरा स्टेल काटला अच्छा अच्छा ओके MTR வரணும் என்ன சார் சரி அப்ப நவீன் உட்காரு சரி MTR
Good morning, Dr. Sanjay. It gives me immense pleasure to be part of this topic. Before commencement of the presentation, I would like to thank the management for giving the opportunity. And my presentation is based on nanofibers and their applications. Of course, I could see the versatile researchers here, but I would like to share some of my views which I have personally experienced. So, we used to say research. Actually, it's research. I would have to start with that. So we have to find out again and again, step by step. In that aspect, nothing is outdated. It has to be updated. So in that concept, here you can see some of the nanomaterials, which is in different forms, and these are some updated. So as I mentioned earlier, you have to update. And we know most of the researchers, they are manipulating the data. Actually, according to Richard Feynman, is the American physicist. He has given the idea of the manipulation. Actually, physically, we can do manipulation. The atomic and molecular level can enhance the properties and we get some proof properties also. So in that concept, of course, we are familiar with this. This is lotus leaf. When we pour the water over it, it won't wait. Actually, it absorbs. In the term itself, that's a manipulation. Absorption, actually. Instead of B, it is manipulated by D, that is absorption. So it absorbs actually, and it is called self-cleaning effect. And whatever we are doing, we are mimicking from nature. So I have some right word instead of image. Since whatever we are doing, we are mimicking from nature. Even for man also, we are mimicking from the lotus leaf and some other things also that we can discuss. I hope I am audible. Yes. So as I mentioned earlier, in the lotus leaf also, absorption is which is undergoes a self-cleaning effect. And if you have given results, because it's also when it works over the walls or anything over the leaves, there are some self-cleaning effect. And if you look at the butterfly, how different color pigments, that's also because of nano. Since the scientists are interested in manipulation in the atomic and molecular levels, and which gives the fruitful output, and they have got the new results when we examine the feathers of butterfly, the structures about nano. So not only butterfly, if you look at peacock feathers also. So that's why I used to say repeatedly, whatever we are doing, we are mimicking from nature. So in that concern, I can spend some time with the nanofibers. As I mentioned earlier, again we have to update. So nanofibers are, of course, we know it's one-dimensional material, and normally the diameter would be 1 to 100 nanometer. There are different techniques. If you see the image, it's a human hair placed over the nanofibers. It's a normally if you take human hair and if you slice it, it has 80,000 nanometers. And there are different techniques available to make nanofibers, in which I have mentioned some techniques alone. The first technique is self-assembly, and second one is phase separation, and we'll spend much time with the electrospin. Actually, in 1874 itself, electrostatic spinning that was updated, and now it is electrospin. Initially, it is electrostatic. Now it is electrospin. And as I mentioned earlier, we are mimicking from nature. If you see these spider dragline, that dragline itself has 3000 nanometers. That is also the key factor for the research. And even cotton candy also the inspiration to make nanofibers. Is one of the next properties of nanofibers. So there are some important properties like it exhibits low density, large surface area. Of course, nano people can understand the large surface area to mass as well as volume. And the diameter is about 52,000 nanometer. And the other properties like it has high pore volume. And if you take physical properties, it has large area, it has high weight, thickness, permeability, and strength. So these are some important parameters. Anyway, we'll discuss in detail in the upcoming slides. And the most important property is filtration property. In other words, we can use mask also based on the nanofibers. And this is some basic idea. Materials used for the preparation of nanofibers. So if you take natural materials, collagen, cellulose, silk fiber, so many materials are available in nature. And if you take synthetic polymers like polylactic acid, polycarbonate, lactone, and so on. So these are some fiber materials, that is synthetic polymers. From that we can obtain the nanofibers. So whatever the method we are adopting, in which the principle is resolution rate. Anyhow, I can explain it later. And there are some recent techniques that also I can explain in the upcoming slides. But before discussing the different techniques, we can concentrate on the unique properties of nanofibers. So the size plays very, very important role in order to make the required efficient nanofibers. And surface to volume ratio. Since we know if the surface is more, we can do more with the surfaces. And these are the methods. I have shortlisted very few methods here. In which the first method is drawing method. So if you prepare the polymers which is in liquid state, like solution rock, we can withdraw it by means of some micropaper. So that is what drawing method. So for your reference, I have mentioned some images here. The solution is like a droplet. You can withdraw therefore micropaper like layer by layer. So based on our requirement, we can withdraw it. So that is the drawing method. And second one is template method. So in the template method, based on our requirement, like a crucible, we can use some crucible, standard crucibles like this. It is also based on our requirement. So in this, we can choose the starting materials and we can extract the nanofibers. And next one, that is phase separation. So in which, when we combine the polymer with the solvent, it can undergo some interlinking like physical linking or chemical linking. And based on that linking time, we can extract required nanofibers. And the most important and easy technique is electrospinning. That's what I said initially towards electrostatic spinning. Some updated and the easy method is electrospinning. So in which the surface tension of the polymer droplet is worked on by the applied electric field. That is the key point in the electrospinning. See, when I was a school teacher, I used to teach some physics for the 12th standard. I took some chapters like J.J.Thomson method as well as oil drop method. That time I did not understand what exactly the concept, but when I go through this concepts, the surface tension and electric field concepts, I can follow it easily and it is very useful. I hope you can also understand. Even I have completed 6 days. During the college days, I have prepared only for exam point of view. But later on, when I start to teach, I have learned that. Even now, I hope when I share with you, definitely I can learn more. So, the second important process is while drawing the fibers in the electrospinning method, it forms like a cone. That cone is called Taylor cone. And further, if you elongate that Taylor cone, we will get the jet, fiber jet. It forms like a V. And the next to spinning, I will spend some more time with the electrospinning. The next technique is bubble spinning. In this also there are further classifications of bubble electrospinning and blown bubble spinning. Other techniques like centrifugal spinning is like normally if you give the blood for any test, they are doing some centrifuges. So the same method, centrifugal spinning, and finally freeze drying. So we'll go with the electrospinning in detail. There are some important parts like syringe pump. This is very important, essential part. And high voltage source, So based on the collector as well as the high voltage you are applying, you will get the different size of nanofibers. And during that process, there are some regions in which four important regions. The first one is the base region, where the charge in the bottom of the nozzle, at the end of the nozzle, Taylor tool. And further, if you are elaborated, you will get a region which is called jet region. And after getting the linear type of layer, can be further split into number of fibers, which is called the splay region. And finally, you can collect it by some collectors, suitable collectors. That also based on their adhesive property, and that is the collector region. This is for your information, and you can see visually like the syringe and where you are applying the high voltage, and finally you can collect the nanofibers by means of collectors. As I mentioned earlier, based on the adhesive force you can collect, and the distance also plays very important. That is between the nozzle and the collector. And this is the oldest electrospinning technique. And this is how we will get the product. The collector will get the product like this. So this is one layer of fiber, and it's for your reference. I have given polyethylene oxide, which is dissolved in water. But you can choose different solvents based on the solvent you are choosing. You will get different properties. Since the conductivity of solvent plays very important role in order to get required nanofiber. And this is the reversed image of one fiber. And these are some images for your reference, which is natural nanofibers. And this is synthetic polymer nanofibers. Again, the experimental set why which is again means in order to explain the Taylor cone, where you are extracting the fiber. Just look at this Taylor cone. It is a droplet. When you elongate it, gradually it's drawn and you get the jet. It's like a layer, and then it's furtherly split into number of small layers, which is called nanofibers. And this is the actual image. This is the Taylor cone and how you are extracting it, and in which how the viscous force as well as the electricity is very important. As I mentioned earlier, in the medical noise drop exclude. I have hardly the idea of this electron I have realized. And these are some important parameters we have to consider while preparing the materials. Like if you take solutions, right type of solution we have to take, the conductivity of the solution also plays very important role. As I mentioned earlier, the key point is the resolution rate. And so based on that, we have to choose the right solution. You can go with the acetone, distilled water, orthographic solutions also we can choose. That's based on our requirement. And the choice of materials also plays very important. And the polymer type, that's what I said, the choice of materials. And the molecular weight, if the molecular weight is high, you can enhance more properties. And the concentration also plays very important role. And viscous solution also plays very important role, and surface tension and electrical conductivity. But in the electrospinning conditions, the important parameters, as I mentioned earlier, like applied voltage, flow rate is very important, and the environmentals, both like the temperature we are adopting and humidity. And the targets while preparing the nanofibers in electrospinning parameters, the diameter of the fiber must be consistent and controlled. That is the important point we have to consider. And the fiber must be defect free or defect controlled. That is also plays very important. Sometimes if it is not controlled, it breaks and we couldn't get the acquired fiber. And the continuous single nanofiber must be collected, or else we couldn't get lengthy fibers. And in terms of solution, the important parameters like the viscosity, conductivity, and molecular weight, that's what I have shown in the previous slide, surface tension, polymer structure, and solution properties. See, in order to give some confusion, if you are choosing the high viscosity of solution, we will get the larger diameter fiber. And if the concentration high, again we can gradually increase the diameter of the fiber. And if the molecular weight is also high, you get the good thickness of fiber also. Actually, compared with the nanofiber, say for example, if you take the spider dragon, the steel fiber, comparing the steel fiber, the spider dragon is much stronger than the steel fiber. That much of thickness and hardness it has. So that's why you have to choose the right material which has high molecular weight. And viscosity is high, of course, you will get a good nanofibers. And there must be there is low surface tension and conductivity should be high. That's why I already explained. This is the processing parameters. We have to use high voltage and as I mentioned earlier, the distance should be optimal. Where we are collecting the nanofibers from the tailor and the flow rate must be high low. If you are increasing the flow rate, then you will get leader. It's not a fiber, you get like bubbles. So in order to avoid that, we have to choose the optimum flow rate. And collector, normally we have to use aluminum material, or else, as I mentioned earlier, the material which has high adhesive force can collect easily. And the ambient parameters are like suitable humidity and temperature, and the solution temperature also should be proper, and the air flow rate also should be proper. And this is for your reference. If you are changing the concentration, you get different nanofibers. And this is the graph between the concentration as well as viscosity. And this is again for your reference. If the viscosity is too small, we'll get different types of nanofibers like this. But based on our requirement, we have to choose the right viscosity. And this is another reference. If you are changing the applied voltage, for example, if it is 10 kilovolt, then nanofibers about 260 nanometer. And if you are increasing the voltage like 15 kilovolt, and fiber is about 220 nanometer. And further, if you are increasing 20 kilovolt as well as 28 kilovolt, you will get the optimum size of nanofibers. So finally, if you increase the applied voltage, you will get this reduced diameter nanofibers. This is also based on our requirement. And this is what I said. So if you are choosing your syringe like this, then you can see it's fine to plane. We'll get one by one. Or else you can choose instead of the needle, you can choose both are plane. So it is plane to plane, and we'll get more number of fibers at a time. And this is how actually we'll get the nanofibers. So you see the second image, you'll get clearly. See, both are point to point. So this is the collector, again this is also point type of syringe we are using. So we'll get high rate of nanofibers. And different types of collectors here. This is also based on RF. And here this is the key point. Where we have to, what are the parameters we have to reduce and what are the parameters we have to increase. See, in order to reduce the fiber diameter, the concentration should be low and viscosity should be low. Injection rate also should be controlled. Whereas applied voltage should be high and needed to plane distance should be high and solution temperature also. So these are the important points we have to use. And just look at this. This is another important nanofiber, that is polyethylene oxide. We can see instead of plate, we can extract their mass. So I hope you can see the nanofiber. And the next important idea is characterization of nanofiber. So I have planned to explain the characterization in case the number of audience or research considered to be useful. Then we will see the next occasion. See, if you see the characterization, like chemical properties can be from the FKR, NMR, and DS will get some idea. And from the geometrical characterization, we'll get the fiber diameter distribution, fiber orientation, Of course, we'll get the morphological information from the secondary. As I mentioned earlier, mechanical properties plays a very important role. So for that, it can be subject to various mechanical characterization. And regarding the physical characterization, like air and vapor transfer properties can be measured. Regarding the structural characterization, we can go. It can be subjected to morphology, fiber diameter, pore size, and porosity. And for optical microscopy, of course, the fiber diameter can be calculated. Diameter distribution also can be calculated. Mostly, I would like to spend some time with the optical microscopy. The people who are doing some optical microscopy, like normally if you take the UV data, we used to calculate band gap, but from the UV data itself will get the purity also by plotting the graph that is called Albach plot. Recently, I have submitted on paper, it is only based on UV. So, from the UV data itself, we can interpret more. And regarding the structures, morphologically, we will get cell, and from 10 marks, we will get again fiber diameter distributions. Furtherly, the updated versions, AF from again we'll get the fiber diameter distribution in advance. And STM, of course, we know it gives the atomic level, and XRD, because we not find out the structure, precise structure, and also that's constants. Further, it is subjected to wide angle extra diffraction. See here, if you characterize the fibers to wide angle extra diffraction, we get the extra formulas. Of course, we'll get from the powered XRD also, but here we'll get some updated information. And patterns of calipers and fibers also will get from the wide angle. Whereas small angle extra diffraction will get organized particle size. Of course, some people can measure from the powered XRD also, but here we'll get some updated information. Shape of the nano fibers also will get from the small angle extra diffraction. Distribution and surface to volume ratio also can be determined for the small angle extra diffraction. But still, if you want to find out the pore structures, we can subject to mercury pores. And regarding the chemical characterization of nanofibers, it can be subjected to various FA, FT Raman, because Raman also available, and NMR also. I don't want to spend much time with that. When it is subjected to mechanical characterization, we can measure the tensile, compression, bending, and shear. Of course, torsion also plays very important role. And furtherly, when it is subjected to thermal characterization, mostly we used to measure the decomposition stage or the heat point. But we can find out some more parameters like enthalpy, entropy from the same thermometric analysis. So, in case if you are interested, just we can have a discussion on it. That is called the Coates-Redfern method. Using that method, we can calculate various parameters like enthalpy, entropy, activation energy, and so on. The other important characterization is wettability and contact angle. Of course, from the wettability, we can measure the filtration property as well as bioimaging property. If the contact angle is less than 90 degrees, then the pressure difference across the interface is positive. And if it is neutral, the wet angle is close to 90 degrees. If it is greater than 90, then we can say it's hypertrophy. These are some applications. The nanofibers are used in tissue engineering, medical applications, drug delivery, cancer diagnosis, and air filtration. Based on the air filtration, it is used in this case it is used in mask. That's what I said. No, for the environmental protection, we can use the nanofiber filtration and biomedical tissue implantation, bone tissue, skin care mask, and wound dressing, drug delivery. In for the defense, they are using protective clothing. Military people, they are using protective clothing based on the nanofibers. I'll show from images also. These are some informations. Yeah. Regarding the wound dressing, just look at the image. Look at some. See, we don't want to use normal dressing materials. Just you can use like a scanner, and we can spray the nanofibers. So that is what wound dressing. Another important material which is used for roborats, especially during some disasters like earthquake. The buried materials can be identified, or even we can get some alert also using roborats, which is based, that brain is based on nanofibers. This is the image regarding protective cloth where defense people are using based on the nanofibers. There are some other applications like nanosensors, like thermal sensor, piezoelectric sensor, biomedical sensor, and so on. And in military production clothing also. The thermal chips also can be made based on the nanofibers PLA techniques. Finally, it has wide application. The energy storage is also like a fuel cells, capacitors, supercapacitors, and batteries also we can use the nanofibers. These are some information regarding fuel cells as well as supercapacitors. And also it is used in dye sensitized solar cells, and recently they are trying in power transmission lines also. So, due to its lightweight, stronger, and low cost, of course, it has high emissions. Any queries?
How to identify the particle size using say diaphragm?
So normally, curve formula they are using.
That is not possible to do.
Yeah, that's why we are using some.
Because that is fiber. No?
Yes.
Very only we can get the particle size.
So that's why we are going for the advanced solution. That's what I said. Fiber diameter can be easily measured. That's from optical spectroscopy. There are different
Only using for the spherical.
yeah, that's what I said, sir. We know powder oxide is older. Now there are some new versions available. Directly we get diameter. By examining the sample itself, directly we get the information. That's what advanced solution.
Really serious. Color depends upon the nanofiber. You said no, sir. The color depends upon the nanofiber. Which color, sir? Butterfly is.
Yes, sir. Actually, it is when we examine that, it's based on the size, different pore size. Some interesting results are there. If you want to discuss, some interesting results are there.
One more thing, sir. How we can confirm the nanofibers are which
No, I have mentioned what are the possible characterization techniques. So based on our requirement, we have to use it. We don't want to characterize all the characterizations which I have mentioned. Based on our requirement or based on the interpretation we have.
Last one, sir. UV you said no, sir.
Yes.
Only by using only we can confirm the purity of the compound.
We can correlate also. So for example, in case if you are measuring the purity by means of HRXR, high resolution X-ray data, that result we can correlate with the UV data also. We'll give some strong information. So that's what I said. See, mostly we are keeping those data. We can correlate from the same data we can interpret more. That's what I'm thinking.
After purification only we can go for UV no, sir.
Of course, sir. We can give some strong evidence. That's why from the same data we'll give some more information.
It's possible to capture high temperature
Of course. See, that's what we are measuring. it should be subjected to various thermal characterization also. Even I would like to spend some time like no, he can be subjected to laser threshold studies also. How much he can withstand. So that's why the choice of materials based on our requirement. Based on our requirement, it has high hardness, but temperature doesn't. We have to choose the right. We can subject to thermal properties also, but then we'll take some information. But high temperature is obviously.
Thank you very much, sir. On behalf of our department, I am very grateful to Dr. P. Krishnan for his valuable information. Dr. Krishnan is a very good researcher. He has published so many articles. So he is more interested in research and publishing more articles. So anytime you can contact him. So thank you very much, sir. When I asked him, readily he accepted. So we are really grateful to you for coming to our institute and delivering your lecture.
Thank you so much for your patience.
May I request Dr. P. Padmavati Madam deliver your lecture on fuel cell technology. Madam is from Caltech University. She is expert on fuel cell technology. I just want to listen.
Good morning, everyone. Myself is Padmavati. Now I'm going to see about one electrolyte membrane. How many of you are relevant to your fuel cell results? Is it anyone? Fuel cell. What kind of fuel cells? Biofuel cell. Anyone? That means no doubt will come. Okay, sir. Sir, உங்களுக்கு காப்பி எடுக்கிறேன் சார். Fuel cell is nothing but it's electrical device which can convert the chemical energy to electrical energy. Similar to battery. But in the case of battery, once the storage capacity is low, we have to throw it out. We cannot use the substances. But in the case of fuel cell, as long as you are supplying the chemical energy, it can able to produce the electrical energy. That is the advantage of the fuel cell. And also, when we are using some other renewable energy resources like petroleum or something, we can get carbon dioxide as the byproduct. And in the case of fuel cell, only the heat and water is the byproduct. That's why it's called eco-friendly energy sources. So fuel cell has been classified into many categories like alkaline fuel cell, proton exchange membrane fuel cell, proton exchange membrane fuel cell, otherwise hydrogen oxygen fuel cell, or quantum electronic membrane fuel cell. You can call it as anyway. And that methanol fuel cell, phosphoric acid fuel cell, molten carbonate fuel cell, solid oxide fuel cell. The laboratory normally people are using hydrogen oxygen fuel cell, alkaline fuel cell, and methanol fuel cell. So these fuels are classified based on the operating temperature and the electrolyte what we are using. So now we are going to see the hydrogen oxygen fuel cell, otherwise polymer electrolyte membrane fuel cell. The heart of the fuel cell is MEA, membrane electrode assembly. Anode, cathode, in between we have the electrolyte, that is polymer membrane. The anode side we are supplying hydrogen as the fuel. So it is spread into the electrode area. Electrode area we have the catalyst, platinum. It is supported by some carbon-based substances. So that it is splitting into protons and electrons. The protons can pass through the electrolyte, the electrons can pass through the external sector. The cathode side we are supplying oxygen as the oxidant substances. It is reacting with the upcoming protons and the electrons so that it is producing only the water molecule as the byproduct. So we have anode part, cathode part, in between the electrolyte polymer membrane. And the electrode part we are having platinum as a catalyst substances. So when comparing to hydrogen oxide fuel cell, method of fuel cell, anode side we are supplying hydrogen as a actual means it is hydrogen oxide fuel cell. Instead of using hydrogen, we are using methanol, it is named as methanol fuel cell. So this is the part of the fuel cell setup. In between, this is MEA, membrane electrode assembly. This is the part of the fuel cell setup. And on the other side, we have gasket and the graphite plate. It is the serpentine flow part. It is flow part for the gas. When you are supplying hydrogen, it will flow like that. And then both the end side you have air plates. So this is named as MEA. Both the sides we have electrode part, in between we have the electrolyte part. So now we are going to elaborately see what is electrode part, what is electrolyte part. Normally people are using Vulcanex 72. It is nothing but it's a trade name, amorphous carbon black as a supporting material for the platinum catalyst. We know that platinum catalyst is very costly as gold. So it should have some supporting material, that material should be electrolyte connecting node. So amorphous carbon black is very cheap and has higher electrical conductivity. That's why people are using that material as a supporting material for the platinum catalyst. But when you are doing the fuel cell performance for longer period of time, the carbon may corrode into carbon dioxide that will poison the platinum catalyst. So to avoid such kind of problems, people are going for some other supporting material like carbon nanotubes, carbon nanofiber, graphene. So we will see one by one. So this is already discussed. So we know that all the carbon supporting substances are chemically inert. So if you want to load the platinum, it should have some anchoring states. For that we need to be functionalized. So functionalization process can be taken by a chemical process. Here I have used strong acids like the azotic acid and nitric acid to optimize the condition 1 hour, 3 hour and 5 hour functionalization time period you have taken. So that afterwards we are getting the functionalized material carbon nanotube. So that only you can load the platinum. The same way we are preparing the graphene. We know that graphene prepared from the graphite sheet. Graphite sheet means arrangements of many layers. So if you are increasing the layer distance, that is the graphite sheets. So straight away you cannot prepare the graphene from the graphite. It should be functionalized one. After functionalizing, it is named as graphene oxide. So that Hamas method, you can prepare the functionalized graphene sheets. If you are here, you can able to see many functional groups are there. So it will absorb more water molecules. So we need to be reduced. That's why it should be reduced by hydrazine so that we are getting graphene as a supporting material. And another one carbon supporting material is carbon nanofiber. Carbon nanofiber prepared from the electrospin process, for which I have taken PAN, polyacrylonitrile polymer. It should be dissolved with a suitable solvent. Using electrospin process, you can able to produce the electrospin polymer fiber. Once we got the polymer nanofiber, it should be stabilized. The stated we cannot carbonize. We know that without material, immediate sample carbon based supporting material need to have. First, we need to be stabilized. In a normal muffle furnace, we can stabilize around 200 to 300 degrees Celsius. We can use. Once if it is stabilized, we have to use CVD, chemical vapor deposition, for the carbonization process in the presence of nitrogen. This is the chemical reaction, how the PAN fiber shifting into electrospin carbon nanofiber. And coming to fuel cell performance, here we have comparison. First A means platinum and carbon, that is supported by amorphous carbon black. Trade name is Vulcanex 72. A means red color line. This one you can able to see. First we will see the current density potential value and the power density we are getting from the current density potential value, we are getting power density value. We can able to see the pink one is the maximum, pink one is the 5-hour functionalized electrospin carbon nanofiber. We already differentiated the functionalization time period for 1 hour, 3 hour, 5 hour. The 5-hour functionalized particular carbon nanotubes has the maximum power density values. coming to the electrolyte part. Electrolyte is nothing but the polymer membrane. We cannot membrane as the electrolyte supporting material because it should conduct the protons. For this, we need to be functionalized. That means using H plus ion it should conduct. For which using sulfuric acid or chlorosulfuric acid, we have to functionalize. Based on the polymer, sulfurating agent may vary. If you are using polyethyl ketone, we have to use concentrated sulfuric acid as a sulfurating agent. If you are using PACPS, polystyrene ethylene butylene polystyrene, we have to use chlorosulfuric acid as a functionalizing agent. So what are the criteria we need to have if you are saying some material as a polymer membrane means it should have high ionic conductivity, low chemical stability, it should not follow, and good resistance to swelling, and the low permeability to external fuel. If you are straight away combining these two fuels, it may explode, but compared to LPG, the explosive rate may be high. And durability and stability also it should be understand, and cost wise it should be cheap. So commercially available Nafion is a high potential one, but why we are going for some other hydrocarbon based polymer membrane means we know that Nafion is nothing but PTFE, called tetrafluoroethylene. We have that fluorine background. It's not eco-friendly one that we know. And also when we are preparing the Nafion membrane, we cannot prepare, it's a commercial one. During the preparation of the Nafion, there is a possibility to explode. So to avoid such kind of problems, we go to some other hydrocarbon based polymer membrane. So this recommends we already seen. So perfluorosulfuric acid, fluorine background membrane, Nafion membrane is available, down membrane, acid membrane, O membrane. And the people nowadays are going for hydrocarbon based aromatic polymer membrane, sulfonated polyether sulfone, polysulfone, and PACPS, some other membranes. So these are several types of polymer membranes. So now coming to the peak, polyether ketone polymer membrane, it should be sulfonated using sulfuric acid as a sulfonating agent. Once we sulfonated means that ionomer should be dissolved in the suitable solvent like NMP, N-methylprednisolone, and pour into the petri dish using like hot air oven. You have to heat so that we can able to get the polymer membrane. That membrane should be dry and use it for preparation of MEA, membrane electrode assembly. And when going for some other blended membranes, we have first what we said we can use Nafion membrane. So it has come in background, so that kind of materials we cannot use. So we are going for some other hydrocarbon based polymer membrane. But afterwards also people are going for some other blended membrane or composite membrane, some other membranes, because this straight peak or SPACPS membrane will have swelling property as well as the stability is somewhat less when compared to the commercial one, Nafion membrane. So that people are going for some blended membrane. Speak membrane, speak is nothing but sulfonated form polyether ketone. So speak is combined with the polysulfone membrane. So here also you can able to see 8% and 4% of polysulfone blended with the speak membrane shows the 51, 37.5 what per se centimeter squared as the power density values. And when we are comparing with the Nafion and the speak membrane, it is showing the 46.5%, and the speak percent speak is 16 milliwatt. It is very less when compared to the blended membrane. And it is speak blended with the PVDF, polyvinylating fluoride. So here also the blended one shows the maximum power density. And this is speak with polyether sulfone membrane. Here also the blended one shows the maximum power density compared to the commercially one and the pristine one. And coming to the PACPS, so this is the pristine polymer, polystyrene, ethylene, butylene, polystyrene. It is sulfonated using chlorosulfuric acid, so that we are getting the sulfonating groups. It is only using the proton transport via Hawking mechanism. So it has high conductivity, proton conductivity, flexibility, chemical stability is also high. But it has some swelling capacity. That's why people are going to pass some other composite or blended membrane. So here we can able to see sulfurated form blended with the crystalline polymer also. So the 5% and 25% shows 5% shows maximum core density when compared to 25%. And the PCPS with the polysulfide. So this is the first one, the strength is PCPS. Second one is the Nafion. When compared to Nafion, SPSCPS shows the maximum core density. And here 2% and 10%. Here also 2% shows the maximum core density. We not only know when they are increasing the temperature, the performance will be little bit improved. Here we can able to see this is 60 degrees Celsius. This is the room temperature. Room temperature shows 21 milliwatt and here 26. For the Nafion also at the room temperature 27 only, but there 34 milliwatt. So if you are increasing the temperature, the performance may be increased. So coming to the conclusion part, when we are using for the commercially available in the name of electrode part, when compared to the pristine carbon supporting material as well as the commercially available Vulcanex 72, the functionalized one shows the maximum power density value. When we are always saying the 5%, 5-hour functionalized one is the maximum power density value. If you are increasing the functionalization time period for 7 hours and 9 hours, it may increase immediately. But the stability may degrade. Using the TG, we can able to see the polymer stability get deteriorated. That's why up to the 5-hour functionalized one shows the maximum power density. In the case of electrolyte part, compared to the commercial Nafion membrane, the Nafion is the good one, but we have the fluorine background, that is one, as well as cost wise per square centimeter it says $750. So it is very high when compared to the other commercially synthesized PEEK as well as PCPS membranes. Thank you.
Any queries?
Even the subjects forget on.
Excuse me. You have mentioned the functionalization part, current density versus functionalization. Can you tell how much percentage is functionalized?
How much?
You have mentioned 5 hours.
Ah,
Do you think that 5 hours or 3 hours, 2 hours, how that functionalization percentage is increased?
percentage increase we cannot say that. After functionalization, the proton conductivity value will increase.
Based on functionalization.
Based on
Number of
functionalization.
functionalized group.
Yes, sir.
So
The
that
proton
number of
conductivity will increase.
functionalized, how do you get calculated? It's mandatory.
Yes, sir. Functionalization we cannot able to see. Using the functional group, whether it is there or not, we can able to see from the FTDR. But the functionalization, whether it is increased or decreased, that we can able to see from the proton conducting value. Siemens per centimeter, we can able to see the values. So that the thing you can able to get, and ion exchange capacity values from the lab experiment, we can see if the functionalization process is increased, we can see the values also will increase.
Yeah, we
But
can get it from surface area analysis, ma'am. The
Surface
surface
area-
area
that
function
is
means
after-
the surface area will be increased.
And that is bed method also. That is what the sir asking is functionalized.
Yeah, the normal material if it is functionalized means the surface area will be increased.
That is also I have. Bed method.
Yeah, we can analyze from that.
Then what would happen if we increase further from 5 hours to 6 hours, 7 hours?
That I will let you know. In the DGA graph, the polymer stability may deteriorate.
At what temperature?
Around 200 and all it will deteriorate. 150 up to you can start. By which it is not start.
Functional group வந்து electron chemistry.
So electrochemical also you can function.
Which one, sir?
Instead of chemical method, using electrochemical method also different calculation of that.
Which one, sir? Carbon supporting. Yes, sir, we have. But what are the things we have in the lab that will be getting?
But again, in carbon-based material like carbon nanotube, graphene, activated carbon, those materials efficiency wise is lower compared to platinum, right?
Platinum is a catalyst, sir. This is supporting material. Platinum itself we are using. So platinum is very high costly, you know. You should have some supporting material. That material should be along with the conducting one. Conducting one means we can go for some carbon based. Commercially, amorphous carbon black is there. But when you are doing the fuels and performance for a longer period time, it corrode, it is poisoning the platinum catalyst. So such kind of problems, people are going for some other carbon supporting material like the carbon nanotube, carbon nanotube.
You have mentioned in modified Herman method, I'm sorry actually. In modified Herman method, you have mentioned that directly we can get it from graphite from graphene. But is it possible to get graphene directly? But if you are going to use modified Herman method, we can get it from graphene oxide, I think GO. After that, only we have to release the oxygen functional group. Finally, we get it from that RGO. We are not getting from directly graphene.
Yes, we are not getting, sir. Reduced
You have mentioned that the graphene, so that's
graphene. First we are having graphite, and from the graphite using Thomas method, we are having functionalized group. It is named as graphene oxide. We have many functional groups.
We can release the functional group. It will be RGO.
RGO is the graphene. If the space interlayer distance is increased, means the van der Waals force may increase. That means we are having single sheet. It is named as a graphene.
Thank you very much. Yes.
Instead of napkin, we can use cytosine. Cytosine.
It is a normal polymer like PSP. If proton transport, but it's in the high
Cytosine also regularly used. Nowadays, many researchers are using, but it is not finalized. There are so many polymer membranes, many researchers are doing biopolymer, synthetic polymer. Universal technology, biopolymer, the membrane is one of the main parts.
Yes, sir. PDA like around we are having, but the stability wise it is not industrial. When we are using in the hot press, we have another and cathode and between three things that has to be hot pressed. When you are hot pressing, the electrolyte part may degrade. If it is not withstanding that much temperature, that is the major problem with all other polymers.
Mostly these people preparing the membrane and studying the conductivity, ionic conductivity, electron conductivity, and the concentration really. And the functional group, other part that is chemistry part. Mostly we are not interested in that part. Okay, madam, thank you very much for your very deep presentations and the new ideas on fuel cell technologies. Nowadays, people are doing research on many energy storage devices, battery, primary battery, secondary battery, supercapacitor. So, fuel cell technology is the advanced technology. So, thank you very much. I hope all the faculty members use the knowledge. Now, I request Dr. Bhavi to tell us what
Warm greetings to all the gathering. Now I take this privilege in thanking our special chief guest Dr. Padmavati ma'am and Dr. Krishnan sir for spending their valuable time in our campus. And I also thank and I'm very grateful to all the HODs and professors and research scholars, those who have spent your time and come over here to get the knowledge of the current happenings in the research field. And without thanking our director ma'am, principal sir, this event would not be a successful one. And let me thank everyone for being here. Thank you.
Thank you very much. Later we receive the participation certificate from all the